the idea of the course is just to, it's basically to present a point of view of computer music or computer music technique, which focuses on basically the two elements that you can think of as being at the root of all computer music, which is distortion and feedback. That's a pretty wild claim. Other people might claim that there were roots like in music and computers or other kinds of things like that. And so my reason for thinking that the right way to, at least for the purpose of the seminar, a good way of splitting it up would be talking about distortion and feedback, is that if you look at the well-known techniques for doing computer music, with the exception of frequency domain techniques, which I think don't really fit into this paradigm at all, you can actually find out that everything that people ever do is some combination of applying nonlinear functions to stuff and feeding stuff back around. That explains oscillators, filters, reverberators, plus it explains all those wonderful things like fuzz. And it also explains a bunch of traditional computer music synthesis techniques that don't get taught anymore because they've been forgotten about but are still important. So the idea is to try to come up with a sort of a unifying framework behind how to think about running things through nonlinear functions and feeding stuff back. And it's going to turn out that there actually isn't a good unifying framework for this, which is good news because it means that the course can actually function instead of just solve the problem and die. There are at least 3 and maybe 4 different, fundamentally different approaches to questions about feedback and nonlinear transfer functions, which you will find if you look at the syllabus, which I can't see, and I can't remember what they all are, but they've been used in different, the ideas of feedback and nonlinearity are used in different kinds of fields in radically different ways. The one that jumps into my mind right now is control theory, where the basic idea is you want to control, say, the temperature of your house. And so you put up the thermostat, you sense the thermostat, and you see what the temperature of the house is, and then you adjust the heat until you get it to where you want. So that's a feedback circuit. And the theory that people study to understand this is called control theory. And you have to learn it in order to be an engineer of certain kinds, like in mechanical. And it actually turns out that the way you set problems up in control theory is radically different from, for instance, the notion of feedback which you would use in order to design a crackle box, which is essentially an anti-control device. And yet it also uses essentially feedback and nonlinearity to accomplish what it does. So I'm not sure I'm going to be able to get to the crackle box this quarter, although I will try. What I'm going to do the first couple of weeks is just talk about distortion, although it's the second of the 2 things in the title. It turns out to have to come first in terms of what you do because why? Basically because I can't explain why, I'll just have to do it and you'll see why. It works. And I hope you will actually believe that this is a somewhat logical and orderly presentation of a bunch of ideas. And if you don't, then that's probably more my fault than yours. A thing about this, I'm recording the classes, and the way that's happening is, so you should know that if you ask questions, unless you hold them up on a piece of paper, they will appear wherever I store the recordings. I'm going to try to paraphrase the questions to make sure I understand them and to sort of make sure that they are audible. I have no idea, by the way, if the recordings will be audible. And I'm also taking a screenshot of the screen every 5 seconds, which I think will make it feasible to make a sort of a tagged movie, although I don't really know this. And then, of course, the other thing I'm going to try to do is archive the actual source files. So this is an attempt to get away from this technique of recording the talking head and actually really record the contents. So we'll see. And it will probably fail, but on the other hand, my attempts to actually video lectures have only met with about 75% success anyway, so I'm not actually even worried about failure. I just plan for it. Okay, so the way the story starts is something like this. If you look on the website, by the way, you should see that there is something about the files for the course. And what I have is a wonderful sync command which will throw everything that I'm doing at the website. So if you want any of these files, just ask me to sync and then you can grab it. All right, and so what I'm going to do is get to where I'm going, which is 206, what did I call it? Files. And week 1, like this. I don't know, well, have I synced or not? I don't know. Well, let's sync. Could not, oh, of course I can't sync. I don't have, all right, so everything I just told you is wrong. Never mind that. I'll attempt to make a nice sync after class is over. Yeah, okay, so the basic all right. The other thing I need to do is this. I need to get my way of writing up on the screen happening, which is done like this. How? I guess I do it here. Okay. So now we prepare for several other modes of failure. Oh wait, I didn't want to do that. I want to do this. I wanted to say, do we have Inkscape? Come on, give it to me. I've lost my file. Oh. Actually get one that I prepared so that it should work on the screen. Yeah, sort of, partly. View. Sorry. This is all stuff I should have done if I'd gotten in here a little earlier. Let's get rid of all the stuff in the view. Sorry. This is all preliminary stuff. All right, and when this is all done, I will actually be able to use this as a blackboard and do stuff like this. No, that can't be done because. Oh, great. All right. This is all stuff I fixed last night and obviously has unfixed itself now. We're going to say the width is down to... Wow.
There's a pencil tool if you don't want the calligraphy effect.
Oh, really? Is that what the... No, I wasn't able to find it. And now I can't click on it because I've never understood why this goes on. And my mouse is... Oh, no, here it is. All right, we're getting there. I'm going to have to use the mouse to use the menu and then the pen to draw the equations. And that's going to happen too. All right, this is, oh wow, look at that. Okay, and I still cannot unclick. How did I, and this was happening to me last night too, and I was unable to figure out.
Are the two drivers fighting each other?
Well, oh yes, should I take the, yeah, but I got the pin well away from this, I thought. All right, come on, okay, that's good. Backspace, go away. All right, good, and now can I do it? Yes! All right, this is good. And then we're not going to do thinning, thank you. 0. Why is this happening? All right, we're just going to have thinning today. It's going to be calligraphy.
Yeah, the pencil tool is 2 up.
All right. Yeah, okay. I guess I'm going to do that. Oh, that's not so bad. Well, that's all right. I'll just deal with the fact that it insists on... Gosh, I hate it. All right, how does it work with this? Okay, this is maybe good. All right. See if I can debug some of this before the next time through. All right, so the thing about, okay, so what I want to do is have this going, then I want to have pure data running. Ooh, did that fix it? No, it did. Ha ha ha. Ah. All right, and now I'm going to get pure data up and running. And what side I'm going to put it on, I don't know. Let's go here. All right. And do I want this? Yeah. Okay. So I don't know if you have these files yet because I don't actually remember if I synced anything before starting off today, but theoretically now we have a patching area and a drawing area, and I should be able to do stuff, and it should now be stuff that you can see. All right, I know, okay. All right, so here's the thing about distortion. First I'm going to show it to you, and then I'm going to try to explain what just happened. So the show it to you is this. I'm not going to use the looper just yet. I'm just going to get another output generator, make a sinusoid, OSC, and 110. All right, okay, this is simple pure data patch, which does this. Except, of course, what else have I forgotten to do? Input device, I don't care, but output device I do. Yeah, and that's a bad choice of frequency. Good. All right, no surprise there. Now, if you want to take that and do something nonlinear to it, simplest possible nonlinearity is to square something. Right? So squaring something is doing this. Take the thing and multiply it by itself, right? So here's my tone. And what do you suppose is coming out of here? All right. One person knew that was going to happen. Okay, so this turned into this. Woo, come here. Why? Oh, sidebands. All right, well that's one. Okay, so there's jargon. Every single engineering or science field has jargon about what this is. My way of thinking about this is simple-minded, which is this. Okay, now I have to try and get this thing up top. Okay, so first off, what did we start with? We started with something that looks like this. Get over here. Ooh, man, really?
Is it on a straight line?
I think I really need the.
Yeah, there's the little curvy derby.
Yeah, I think I need this thing, which I was able to figure out how to use. Okay, good. All right, okay, so here we go. Cosine, whoa. Okay, maybe I should know about a nice line tool. Here's a function which is a function of time or of sample number. All right. And there's probably no way to make it not do that, is there? I'm done. All right. Okay. So what's happening here is we have a function which is a sinusoid, which therefore we write as not using the word sine, but using the word cosine. And if you're doing stuff digitally, the easiest way to describe this is cosine times of a frequency times the sample number. So this axis is in the sample number, and it is discrete, which means it actually really looks like a set of discrete points like that. All right? All good. This will all work in the continuous case, but right now we'll just do it in the sampled case because reasons. We'll have to do continuous stuff later when we talk about feedback, because feedback works radically different when you feed something back in sampled world as opposed to in continuous time world, and we'll get there. That's a thing for week 4, I think. Okay. So right now we're just going to pretend everything is discrete time, and we will pay for it a little bit later on because we will enjoy some serious foldover when I start doing real distortion, which we will find out about. Okay. Well, all right. So then, what did we do to? Well, what did this network do? Well, what that did was that gave me, if this is x in, right? So this is a name for this signal is x in, like that. This means x is so this is the axis x, if you like. Gosh, I really can't do this very well. All right, and sorry. Okay, good. And now what you can do is you can say, well, what are we doing when we distort something? That thing is multiplying xn by itself, and so you can describe that, I hate it, as being this function here, xn squared. All right, so now for future reference, let me give you what I regard as the fundamental formula of computer music. And this is something that everyone who's dealt with me has had to learn that I think is the fundamental formula for computer music, even though it isn't really. Here it is. It's cosine A, cosine A times cosine B is equal to 1/2 times the quantity cosine A plus B plus cosine A minus B. Ew, stop that. All right. Why? Well, it's just life. There are the way you can show this. There are two ways that you can show this. The way that you learned it in high school was you actually drew triangles, so that you stick a triangle inside a circle and make two angles, and then you get the cosine sum angle formula, of which this is a rewrite essentially. Or the way you do it if you're studying in the computer music program at UCSD is you say, well, actually this is, whoa, that was interesting. Oh, I see. There's a button on this pen I keep pressing by accident. Okay, so a thing that you can say is this. Cosine of A is e to the A plus e to the minus A, over 2. And then if you just take two of those things and multiply them out, you get e to the A plus B and e to the A minus B in the expanded product, and then everything works out perfectly. And you can see at a glance why this thing happens. Okay, so this particular case of that is the following. If you took this thing and squared it, you would get this. X squared n is equal to 1/2 cosine, now A plus B, let me do A minus B first. Let's actually make a good S. A minus B is 0 because A is omega n and B is omega n. So 1/2 of the cosine of nothing plus the cosine of 2 omega n. That's A plus B. All right, now, who's lost and how is the next question. There are 5 different ways you could be lost. The notation could be messing you up. You could have no idea why this has to do with what I just played you over the speakers. And there's another fundamental thing that could be messed up here. I forgot what the third thing is, and there are others that I can't think of.
I'm lost in a few of those ways.
Sorry?
I'm lost in a few of those ways.
Oh, okay.
I'm going to ask how.
All right. Actually, yeah. If you've ever written a computer program when it doesn't work and because one thing is wrong, you can usually find it. But when something doesn't work because two things are simultaneously wrong, then it's very hard to isolate the problem because the problem bifurcates on you. Okay, let me do this a different way. This might help and it might not. Let's go over here. Get my mouse back. All right. Make this a nice tall window. And start graphing stuff. Okay, so what I'm going to do now is I'm going to put down 2 arrays and I'm going to try simultaneously to show you what these 2 signals are so that you can see what their relationship is. And then I will go back and try to relate it to this equation. Okay, so the way to do that is we go, by the way, way number 3 that you could be confused is you could actually not know how pure data works and therefore not have any idea what I'm doing when I'm making patches. We're still looking for 4 and 5, which are there somewhere, I'm sure. Okay, so I'm going to try to explain what I'm doing patchily as well as actually use the patch to do the thing that I'm doing. All right, so I'm going to make an array. The array is going to be for holding onto these things, and things running at 220 hertz, and I want an array of a reasonable size for holding 2 or 3 periods of that. So what does that mean? Up period is 5 milliseconds, so 15 milliseconds, maybe 1,000 points. It's probably too much. 500 points. Okay, let's find out. All right, there's an array with 500 points in it. And now what I'm going to do is put the signal in it using the wonderful tab right object with an I, which takes a signal and which takes a bang message to tell it to go. And if I haven't forgotten anything, oh, name the array.
Array
Array
1.
Oh, thank you. I really shouldn't name it array 1, by the way, because someone else is going to be using that name. So let's give this, what's the right word? A descriptive name, like signal. How about trace? Scope. This is my oscilloscope, except I'm going to use one because I have two of them. All right, and now I'm going to say scope 1 with an O. And now, got it. All right, good. All right, there's a sinusoid. This is what I was trying to draw here and failing to do very well. Oh, yeah, and here you can see clearly the difference between continuous time, which one uses when one draws because paper is continuous, and discrete time, which is these points, and that's going to bite us later in some way that I have yet to find out about. All right, now, I did that so I can do this. We'll make another one, and it's going to be scope 2. And now I'm going to make a tab right for it. Oh, cool. All right. Good. Anyone know how I can get these two to graph at exactly the same sample? Thank you. Yep. Just see if you're awake. Now I'm going to do this one here. All right. So now what's going to happen is the oscillator is going to go into scope 1. This thing, which is the oscillator times itself, which is therefore the oscillator squared, is going to go here. And then when I click this, you'll see exactly what you hear, which is this. That's scope 1. That's the thing in scope 1, and here's the thing in scope 2. All right. Now, what happened? Okay, so several things I have to... Sorry, I'm just realizing I don't have my notes. That's going to be cool. All right, if I forget what I'm doing, I have to run back to my office and get my notes. All right, so what happens here is whenever this thing is 0, this thing is perfectly 0, all right, but this thing is 0 twice per cycle. It goes positive and negative. And furthermore, it's got a kind of symmetry, which I'll get back to later, which is that the part of it that's below the line is actually the same thing as the part of it that's above the line, except that it's flipped over. That's going to turn out to be significant. In this particular picture, the way that you see that significance is this. Everywhere this is 0, the square of 0 is 0, and so it hits 0. But anything negative multiplied by itself is positive, and anything positive multiplied by itself is positive too. So this thing never gets below the 0. And furthermore, when this thing is negative, it has this shape, which is a half cosine cycle. And that, when you square it, gives you a full cosine cycle, which is lifted up so that it only reaches down to 0 instead of reaching down to -1. All right? Okay, so, all right. So that is a picture of what this is an expression for, if you can read my writing. This expression, cosine of 0 plus cosine of 2 omega n. All right. First off, dirty mathematical secret, the cosine of 0 is 1. So this is really a half of the thing which is 1 plus the cosine of 2 omega n. And cosine of 2 omega n is the same thing, is just a way of saying a sinusoid that is running at twice the frequency omega. Or to put it another way, this is running at a frequency, all right, but it's the frequency 2 omega instead of the frequency omega. All right. Now, the next thing I should tell you is this is cool, but you can't just use this to raise everything up an octave. All right, so why not? Well, let's, at the risk of some embarrassment, let's go get the test signal. Test signal. This is just me trying to play guitar. And that turns into this. All right, so it's gonna just knock everything up an octave, right? Whoops, sorry. Get rid of that. What have I done? Oh, duh. No, that's not right. I need to take this thing and square it. And then, I'm just making you wait for this. Okay. And in fact, okay, now, okay, let me show you what's happening now. Something that I am actually prepared for, but so there's my signal. Recordings, all right, so ears work using, they don't really work using decibels, they work using sones, and the trick is a signal that looks like this is actually almost full blast. It's not exactly full blast, but it's loud enough that it makes a perfectly decent recording, even though if you look at it on a graph, it looks completely disturbingly small. But it really is disturbingly small if you took this thing and squared it, because what that's doing is multiplying it by itself, so that if it reaches up only to, say, a value of 1/10, when you square it, it reaches only up to a value of 1/10 squared, which is 1/100th. So when I took this thing and then squared it, I got very nice quiet signal. Now, if I were not the experienced computer musician that I am, I would now just reach for the mixer and fix the problem. And then I would forget and make a sound of normal loudness later, and it would be bad because these are very good speakers. It won't hurt the speakers, it'll just hurt us. So let's not do that. Let's actually fix the problem where it needs to be fixed, which is by taking the looper. I'm just going to disconnect everything here. Taking the looper and actually giving it a gain. And I gave myself an abstraction called gain. Oh, I didn't. Unless I didn't. Let's see. Tilde? I don't have it. I forgot to give myself the gain abstraction. All right. Am I going to just multiply this by 100, or am I going to go find the gain abstraction? I'm going to find the abstraction, because I want you to have it too. Yuck. Where am I going to go to do this? I'm going to go here. I'm going to get rid of the useless browser. Yeah, I forgot to get it. Okay, so now what I do is... Oh, caps lock. You should not do things the way I do them. This is the mark of someone that learned how to use computers back in the dark ages when people didn't have GUIs and stuff like that. Anyway, any of these puppies will be fine, so we will copy this one down to temp so I can get it later. Yes, of course, I forgot to do the pushty thing. All right, now we go back here and we have, when I sync this, which will require that I go on the network, you'll have this too. Right? Okay, now I say gain, please, and we get the gain thing. I'm actually going to fix the gain thing. I want a lot of gain, so I'm going to, let's see. Oh, it's all right. Let's see, what is it? It maxes out at 120. This is in dB, so multiplying something by 20 dB is applying a gain of 10. And I don't like that. I really want to have like a gain of 100 or so I'm going to probably type numbers at this later. All right, so now we say, ooh, maybe, oh yeah, it's good. We're not doing any output. So now I'm going to square that, which is, okay, 100 dB, all right, so acoustics, 120 decibels. Decibels are a scale that you can set any value to to mean unity that you want. So 120 decibels is not a well-defined value. What 120 decibels means in sort of common PD usage is 100 decibels is full blast, which means unit gain. So 120 actually means 20 decibels of gain. This could be considered user-friendly because what that means is that something like this, which is more likely what you're going to do is attenuate something, gives you a nice positive number like 80 out of 100 instead of a nice negative number like minus 20, which is the way you would say it if you were a sound engineer. All right, now let's see where we're at. Okay, so having done that, I will now listen to the 20 dB louder thing. It gets decently loud. It's probably not loud enough yet. And I'm going to look at it in scope. Yeah, decent. Not terribly good, but decent. We'll be able to hear this anyway. So there's this. And here's the one that's an octave up. All right. Didn't work. You noticed something else interesting, maybe. By the way, I played major chords for a good reason. Maybe I'll be able to explain that later. What happened here? What happened there? Why didn't it just knock everything up an octave? Why does the logic break down? This went up an octave, and sound is made out of sinusoids, so whatever I did on the guitar should be ideally expressed as a sum of sinusoids, and each one of them got squared, so each one of them should have gone up an octave, right?
We're getting the sum and the difference.
Okay, thank you. Yeah, when you square something, if it's a sum of two things, you get the square of the first thing and the square of the second thing, but you also get cross terms. So to put that politely, should I? This is not a good place to write this because this is not in this logical sequence, so I'll write it and erase it. How about that? Here's the thing about cross terms. Ah! Wow, how did that happen? Oh, I changed my width for some reason. But at least I can do it now. Cool, okay. So is this going to work? Okay, so here is the thing. I guess I'm just going to do it. It's equal to a squared plus b squared. That's the stuff that, I don't know, that's the stuff that went up an octave. But then it's also, then you also add 2ab. And that's all right. But now suppose, now imagine, okay, so did everyone follow what this means? If you have a sum of two things and send it into the squaring machine, what comes out is the two things that you put in squared all right, and then you get this thing, which is not something that you put in at all. All right? Furthermore, if this weren't a plus b, but if it were a sum of 100 things, you would have 100 a squared type terms, and you would have 5,050 cross terms, if I'm adding it up right. I think I'm adding it up right. Maybe 4,950. So the cross terms actually would be much, much, much louder than the straight terms in the aggregate. In other words, the straight terms wouldn't even really matter in the large scheme of things. Okay, now what I really should do, here's something you can't do on a blackboard. Let's just take this thing and move it out of the way until we need it later. Now let's put it down here. Ha! Okay. All right, so to show you that in another way, let's do this. Let me get a prepared example out of the PD help files now. Okay, so this now I'm going to save as, because something's going to go wrong, and I'm going to wish I had this back. So this is now going to be 1 dot whatever distortion. All right. Now maybe I can just leave this out, but in pure data, if you ask for the browser, you get a bunch of patches, or you get the browser, which you can use to find your way to a bunch of things. And these things are patches which illustrate theory, which is explained in my book, which is online. So if you want to know about this in detail, go look at the book, and it's actually much more clearly presented. Well, the bit of it that's in the book is much more clearly presented than I can possibly present here. The thing is, I can do a lot more here than I can do in the book because I can do it more freely. But at any rate, at any time I do something nice and safe, which is to say something bookable, then you might be able to find a patch that explains it in the collection of patches here. And here the interesting one is E4, which is the difference tone. All right, so I'm skipping 4 chapters of the basic how to do computer music in order to show you this thing. So this is not a systematic, square one kind of a thing to notice. But this is an important effect, which is exactly what I showed you with the guitar, which is this. Here's a nice, hello. Here's a nice musical fourth. It's a musical fourth because the 2 frequencies are in a ratio of whatever that is, 4 to 3. Is that true? Doesn't look right, but let's pretend that's a 4 to 3 ratio. It probably is. And now what we'll do is we'll start to distort it. Now here I have to apologize because I'm going to go forward and then backward again to well, you'll see. This is a nonlinear function, which is not the same thing as squaring. And the history of distortion actually starts with nonlinear functions that are like clipping as opposed to nonlinear functions like squaring. So what you will hear will be essentially the same effect as, well, will stem from the same fact as what I was explaining earlier, although the specific function that I'm using is going to change. And in fact, today I'm going to be changing back and forth between nice mathematically well-behaved functions like times and nice sounding functions like clip, which are not nicely mathematically behaved. And you just sort of have to you just have to navigate between those 2 possibilities. You can have one or the other and not both. All right, so clipping is another nonlinear function which I will try to graph later on, but which I will now just give you as an effect. So when I push the amplitude of this so that it clips, I get the 2 original tones, maybe, you can still hear them, but I also get a resulting tone, which is the common subharmonic of those 2. If there is a common subharmonic, that might happen. So now if I push this up by a half tone, can I do that? It's only approximate, but now I just managed to make the thing go down to a tone which I hope you hear. Right? So that's the, well, never mind what modulation that is. All right, so what happened is we started out with perfectly reasonable 2 pitches, and then we ended up not preserving those pitches, but instead making new frequencies out of the frequencies that went in. Right? Now, as long as I make these things have a nice rational ratio, then I'll get something with a common tone. And if I make it be something with an irrational ratio, then I'll just get something else. Like that. And that's just, computer musicians call that an inharmonic tone. And people get all excited about inharmonic tones. All right, so that was distortion shown from a patch which you can call back up out of the PD help files or examples, which I hopefully explained in a different way this or exemplified in a different way this effect of cross products or intermodulation between pure tones that went into the nonlinear function. So to go back and show you that in the simpler, or rather mathematically tractable case, let's get rid of this. Oh, actually, why don't I? Yeah, let's do that. right, so now I'm going to go back to this thing where I'm just squaring the sinusoid. Do I want to do this? No, I want to do it this way. So I can keep all my apparatus. Let's drop the gain and just use the oscillator. And let's see if we're still here. Okay, so now we're back to the original nice, safe, anesthetic computer music situation, right? Okay, that's the one which looked like this. All right? Now what I'm going to do is go back to this oscillator and make there be two oscillators that will sum into the gain tilde. And what frequency should I give them? 330 maybe? Okay, so here's one. I can just leave that on. Here's the other one. What interval is this going to be from the original one?
Yeah.
What'd you guess? Fifth. Yeah. All right. So if this is A, oh, why is that so quiet? It's quiet because I have this way down. Then this is going to be approximately E, but it'll be a perfect E. And now if I put them together, why did that just happen? Oh yeah, of course. I'm giving you the sum of the two. So there's one. Here's the other. Those are the products, but then the cross products are this other stuff. All right. Here's the original undistorted sound. Okay. So sorry, that was a cheesy choice of two frequencies, but I'm not going to try to make it more interesting because there's more stuff to do. Oh, right. And of course, if I made this be like a tritone above that, which I don't want to do right now, then you would get something inharmonic. You'd get, well, actually, I should do this because this will be a lot clearer sounding, or this will be a clearer thing than the example I just made. Okay, so 330, got this, and that gives me this. Now if I change this, and that's a sound that those of you who've been around Stockhausen music know that's the ring modulator sound. Why did that do ring modulation? Well, what happened over here? Yeah, what happened over here? Oh, let's do this. Alt, where's my Alt key? Alt. What happened over here was I took two things and added them, and I got the square of the one and the square of the other, and twice the product of the two. And when you multiply two sinusoids, that's ring modulation. That's just the classical way that people do ring modulation. Actually, ring modulation, historically, is just multiplying two signals, but people discovered rather quickly that at least one of the signals probably should be a sinusoid if you want to have a reasonable sounding result. Unless you're Vinko Globokar, go check out his piece for voice and percussionist and ring modulation, where he ring modulates a voice in a huero. It is the raunchiest sound, even in Globokar's repertory. Recommended. And it hasn't been performed here in a while, by the way, in case you're interested. All right. Next thing. So if that was what you got when you squared this, all right, so let me give you a historical start. Let me give you some more framework here. What I'm going to do now is stuff that dates back, I believe, to 1977. So this is stuff that is sort of lost in the past of electronic music. But it's actually an interesting, I don't know, it's foundationally interesting because, again, I think understanding this helps you understand what more modern processes do and how they work. So this is, all right, so we're not going to square this thing, and that was kind of cool. So what now happens when you cube it or raise it to the fourth power or whatnot? Well, okay, so the first thing we should do, since we're good computer musicians, is we should just do it and then see what we get, and then we'll try to explain it, right? Okay, so let's see. I think what I should do is save this and then do a save as. And the next one is going to be number 2. And this one is now going to be polynomials. So polynomial distortion, let's see, let's keep the scopes around to get them out of the way, because now we're going to have to make polynomials. It'll take a little bit more room, maybe. Probably don't need, I don't know. No, it's not. Let's get rid of this, get rid of the looper. All right, so there's my nice A, and we already know what that does. So I'll just have that around, but then I'm going to make a stack of these things that are different powers of the oscillator. So first thing we do is we square it by multiplying it by itself. And that gives me, all right, so this is all stuff we've done already. There's that, and then squaring it does that. Just so you don't forget, squaring it, the part that you heard was the double frequency, but there's a part that you don't hear, which is this thing, which is DC. All right, so really, really you should think of that as being two different tones, one of which you can't hear. All right. So I think this is what's going to happen if I raise it to the third power. Is it going to go up a 12th? All right, let's do it. Have you guessed that I know what's going to happen? Okay, so to cube something, you just square it and then multiply it again. And I'm trying to figure out a way to make this be neat. Let's go down here. And, okay, here's the original sound, and here is the cube. Now, what do your ears tell you is in this tone? What well-known jazz instrument does this remind you of? No takers? That doesn't say Hammond organ to you? No? All right. Now I'm going to have to work harder to fool you guys. All right, let's look at the spectrum. So what I can do now is I can say open spectrum 1. And now I'm going to say send to spec graph. I don't know if this is the best way to be doing this. And what do we have? This, by the way, is yuck, this is an old version. Sorry. And anyway, okay, there it is. Ha! So, okay, so here's the original signal. Whoops, sorry. I need that, but get rid of this. The original signal looks like this, and the cube of the signal now looks like this. So it's got the original tone in it, although later on I'll have to admit that it actually has a different amplitude. And then it has the third harmonic as well. All right, so while we're at it, let's keep that around. And now let's try just going on and on this way. Okay, so that'll be the third power. Here's the fourth power. Here's the fifth power. Go up to 6 maybe. And then it'll get tiresome. It's already tiresome. And then this goes here, and this goes here. And then I'll need one more. All right, let's see. So here we had that. Up an octave. There's my bad Hammond organ sound. Oh, what's happening here? It's up an octave again. All right, so we better get our spectrum graph out and see. Oh, it's an octave with a nice partial. So the one that we had before, sorry, let's get rid of it, was just the octave, and it's not showing us DC because this thing is smart and it filters out DC, although actually that's kind of dumb, really. It should be showing it DC. There's DC in the fourth power as well. And the reason I know that is because the fourth power is also always positive. Anytime the signal is always positive, unless it's 0, it's got some DC in it. Okay. Okay, and similarly, okay, so, and fifth power and sixth power. What's happening is it's picking up more and more harmonics as it goes along. So that the sixth, well, two things is happening. One is alternately you're getting things of the original pitch with progressively more harmonics, but only odd harmonics. And that's the odd powers. And the even powers are actually up an octave and progressively have more harmonics. All right? Well, of course, I can explain all this with equations. So how do the equations look? The equations look something like this. Not sure I'm going to be able to fit this. No, I'll just try. Okay. So then, first, am I actually, let's see, what tool do I want? This one? All right, so I'm going to give myself a little bit more room here. So the cube, sorry, I'm actually drawing smaller than I can really draw here. That's this. It's a quarter times the cosine of minus omega n plus twice the cosine of omega n plus the cosine, of 3 omega n. Let me do one more and then I'll go back and show you how this is happening. All right, so the fourth power is 1/8 cosine of minus 2 omega n. All my bad habits are coming out. Plus, let's see, 3 cosine of 0 plus 3 cosine of 2 omega n plus cosine of 4 omega n. And that's where the series stops because I don't have enough room horizontally to get to the next one. Okay, so let's see. First off, 1, 1, 1, 2, 1, 1, 3, 3, 1, and I'll tell you the next one, 1, 4, 6, 4, 1. People recognize those numbers? Pascal's triangle, which you probably were subjected to when you had to study probability. Prob and stat, which is anyway. Okay, let me show you then how this is happening and why these equations are building up the way they are. All right, so we started with cosine of omega cosine of omega n, and then we squared it, and then what that got was, because of this formula, where's the formula? Okay, the formula's there. Okay, good. So cosine omega n times cosine omega n is a half cosine of nothing plus cosine of 2 omega n. Then, when you get down here, we're going to multiply cosine of omega n again by this whole mess. In other words, we'll take x squared of n and multiply by x of n, whose formula is up there somewhere. X of I should repeat that. So, just for reference, x then is cosine omega n. Okay? So now we're going to multiply cosine of omega n by this. So first off, cosine omega n times the cosine of 0 is cosine of the difference minus omega n plus the cosine of the sum, cosine of omega n. This 2 is because of something else. That just gave us cosine of minus omega n plus cosine of omega n. This is all nonsense because this is actually 1, and we're just multiplying something by 1, but I have to maintain the what's the right word? I have to maintain the rule of the equation so that the pattern will come out. Then we're going to multiply cosine of omega n by cosine of 2 omega n, and we'll get cosine of 2 omega n minus omega n, which is another one of these, therefore 2. And then we'll get cosine of 2 omega n plus omega n, which is one of these. So in general, each of these terms, like this one, gets fed from this term and from this term, which is the way Pascal's triangle is built. Each thing is the sum of the two things that are at a corner above it. Right? So basically what happens when you multiply cosine of omega n by one of these things is each of these terms splits into two, but the splitting terms merge in twos, except for the ones at the end, which remain with 1. And furthermore, you have a nice, okay, so it's a good thing that when n is equal to 0, so that the cosine of omega n is equal to 1, this expression just comes out to 1 as a check. Why? Because it's 1/8 times 1 plus 3 plus 3 plus 1, which is 1. Right? So everything is at least not so fundamentally broken that we can't get 1 back out of it. All right. Now, if you picture what this is in terms of a spectrum, each of these things reaches, well, okay, so these things are centered at cosine omega n in some way, but they are splitting outward progressively, so that at each progressively higher power, the highest frequency that we get goes up by 1 more harmonic. So this has at least 2 good qualities. One is that all these things are band limited. What that means is that there's only a finite number of components in it, and therefore, if all those components are below Nyquist, you won't get foldover. So this is a thing that has 0 potential for doing foldover if you do your homework, which is a good thing. The other thing is that the brightness of the sound will go up as the number of times you multiply it by itself goes up. But actually, if you graph these things, let's see, I don't have a good clean way of graphing this. No, I don't have a simple way to graph this right now. If you graph this, you would see something that looked a little bit like this. I'll just do it and then get rid of it. 1, 3, 3, 1, and then you would get 1, 4, 6, 4, 1, and so on. And these things will actually limit to a bell curve. And the bell curve, why do they limit to a bell curve? Well, because one way of saying it is, the way you studied Pascal's triangle in your Prof and Stat course was you did coin tosses and probability of getting some number of heads out of a certain other number of tosses. And it gives you approximately a Gaussian, but exactly a number out of the Pascal triangle divided by 2 to the n. And the Gaussian is good because what that is saying is that if you threw a coin thousands or millions of times and just aggregated the result, you would see, roughly speaking, a bell curve. The reason I'm bringing the bell curve up is because bell curves have a width, and the width of the bell curve turns out to go up as the square root of the number of times you toss the coin. And that is something that you studied in Prof and Stat when you computed the standard deviation of a sum of random variables. And it's the reason the law of averages works. It's not really, but you can treat it as the reason the law of averages works. If you want to measure the probability of something, take a huge sample, and the measured average will be something close to the real average. But for us, what we care about is this is a nice spectrum. And so we could listen to this, and you could imagine then the spectrum widening and narrowing as the number of times you multiply the things goes up and down. And so you might actually give yourself a nice whammy bar for making spectra. Okay. There's one little thing that I didn't tell you, which I should tell you about this, which is that some of these frequencies are negative. And when you have negative frequencies, those are the same thing as the positive frequencies. Well, an oscillator going backwards sounds exactly the same thing as an oscillator going forward. Because if you took this cosine and reversed it in time, you would get exactly the same function. And in fact, one of the reasons that using the cosine function is better than using the sine function for this kind of reasoning is because if you do this with a sine function, when you turn it backwards in time, it messes up the phase, whereas the cosine really is exactly what it is backwards and forwards. That's a good property. Okay. So what this is really is 1/8 of, well, it's 3/8 of DC plus, and then there's 3 plus 1, 4/8 of the second harmonic plus 1/8 of the fourth harmonic. So this bell curve folds back over onto, well, folds this way to make the actual spectrum. All right. So what can be made out of this? Okay, so the next thing I want to show you is a thing which is back in the pure data repository, which is now, okay, so each one of these things introduced one new frequency, which was cosine 2 omega n, cosine 3 omega n, cosine 4 omega n in series. Now, what would you do? Well, you could use this as a way just of getting the cosine of 2 omega n and the cosine of 3 omega n and the cosine of 4 omega n. And the way you would do that is you would subtract, carefully subtract out earlier ones to cancel out all the other components except the top frequency one. So to go back, suppose I really actually did want to get something that was a 12th above that, which is 3 times the frequency. I cubed it, and I got this, which actually has a component at 3 times the frequency, but also has this other stuff. Okay. So now what I could do is I could okay, actually this is, sorry, what am I saying? This only has amplitude 1/4 because this is getting multiplied by a 1/4 quantity. So if I really want to get this whole thing, if I really want to get just cosine of 3 omega n, what I would do, let's go back to where I can draw, is do this. If I took, let's see, get this up. If I took 4, oh, I'm back to this mode. It's because I'm holding this button down without knowing it. All right. Okay, so what we're going to do is we're going to take 4x to the 4th. Oh, I'm sorry, x cubed. Okay. Now what I'm doing then is I'm taking this and I'm taking 4 of them to cancel out this 1/4 so that we will get cosine of 3 omega n. The problem is I will also get 3 times the cosine of omega n. So I'm just going to subtract 3 times the cosine of omega n, which I already had. This is a simple situation where I just have to subtract one harmonic out. But in fact, if I want to get this one here, what I would do is I would take 8 times x to the 4th and subtract something times x squared, and then I would have to subtract or add in something times 1, and so on like that. And so I would actually be able to make linear combinations of these things, always either the odd ones or the even ones, to get exactly one of these cosines out. And that would be a frequency multiplier. So here, for instance, to actually do that, I would take this signal and multiply it by 4, sorry, the cube, here's x cubed, I multiply that by 4 and I'll subtract that times 3. Right? This will never work. Oops, wait. Okay, so I'm going to multiply this thing by 4. X, and I'm going to multiply the original thing by 3. And then I'm going to subtract them. Like that. And then I'm going to get another one of these things. And if we've done everything right, we get a pure tone up 1/12. So that is this. Oh, and I didn't say what that was, so I should do that. So that turned out to be equal to cosine of, ooh, yuck, sorry. Oh, I'm using the pen backwards, wow. Okay, let's try this again. Cosine of 3 omega n, like that. All right, I'm going to save this collection of stuff, and then I will tell you where you can look to find out about more of this. So we're going to save the copy. And this is going to be, yikes, this is going to be, I don't know. Got to get into 206 files. Now I'm going to call one. I'm going to call this one. Let me type one dot. I don't know what to title this, so I'm just going to call it one for right now. Save. And now when my net comes back, I can sync that out for you. And now what I can do, which gives me great pleasure, is now I'm going to leave this up for a bit, but pretty soon I'm going to be able to select all backspace and start over. All right. So now the next thing I want to do is show you how you actually can codify that. These things have a name, by the way. They're called the Chebyshev polynomials. This is a polynomial which, well, the polynomial is 4x cubed minus 3x, and it's a polynomial which takes cosine and turns it into cosine of 3 times as much. It's a wonderful thing to know about, and they exist all the way up to infinity. All right, so save this. So what I'm going to do now is I'm going to get out the Chebyshev polynomial example, and you will see when I get it out why I just wanted to get it out instead of make it. It's down here. All right, so here it is. Let's get this thing up here and play. Oh, here's the same frequency. 220 turns out to be a great test frequency. Here's the octave. All right. That, I'm not doing that by changing the frequency. What I'm doing is changing the table. And I have to do some explaining here. These functions that you see here are the Chebyshev polynomials. This one in particular is the one that I just showed you, which is 4x cubed minus 3x. And the polynomial is useful in the range from minus 1 to 1. It looks like a cubic polynomial. And furthermore, it's neatly inscribed in a square that is 2 on a side. So you put in numbers from minus 1 to 1 and out come numbers from minus 1 to 1. And the same that same thing about being inscribed is true of all these. In fact, these are exactly the polynomials which are inscribed in the square. So here's the first one, which is just squaring the thing but taking the DC component out. And each time you go up one order, the thing wiggles harder, but it actually always is tangent to the thing on the bottom and the top. Furthermore, it wiggles faster at the ends than it does at the middle. That's another quality of the Chebyshev polynomials. How do you compute these? That's the thing I didn't want you to see. I just wrote out the Chebyshev polynomials as expers. And yeah, you can just do that. If you don't happen to know these numbers on the top of your head, you can look it up in Wikipedia, which probably has the first 20 or 30 of them. And furthermore, this is a thing which takes this tone and when you run it through this polynomial, turns it into the tone which is some multiple of the incoming frequency. Now, okay. So a lot of people got very excited about this in the late 70s because it made it seem like you could make any spectrum that you wanted to. In fact, it's true. If I can make the pure overtones of this tone, then by confecting suitable sums of these polynomials, I could make any combination of partials that I want. And that sounds cool until you reflect on the fact that you can do the same thing just by pre-computing those partials as a waveform and putting it in a wavetable, which also works. But this gives you one interesting thing that the wavetable doesn't, which is this. If you change the amplitude of the oscillator that you put in, it actually changes the timbre of what comes out in a rather strange way. So this is full blast. That's nothing. And between nothing and full blast, you get this. was what was accepted in the 1970s as a computer-synthesized trumpet tone. You can look the papers up. It sounds indistinguishable from a real trumpet. By the way, that hype comes out today. Anytime a new instrument shows up in a music store, it sounds identical to a saxophone. And then next year, no, but this one sounds identical to a saxophone. It's been going on now for 40 years at least. Okay, so here's an identical trumpet imitation. So what's happening here is, all right, I'm calling this the index here. The thing about these polynomials is that they do what you want to do if you put in a unit amplitude cosine. But if you put in a cosine that is not unit amplitude, then what's a good explanation for what happens in these terms? What happens to these things is that they just get scaled differently. But the way you have to combine them to get them all to cancel out and just give you the pure tone changes. And so if you don't change that mix, then what ends up happening is the way they cancel out or don't cancel out changes instead. And so what you hear as the index changes, as the amplitude changes of the sound that you go in, different harmonics come in and out until finally you get a magic moment when they all just sort of focus on that high one. And that is the old computer music wave shaping sound, which showed up in some of the computer music repertory in the 70s and then quickly got forgotten because people didn't know what to do next. But it turns out that there are a lot of next things that you can do. All right, now what I'm going to do is...
And in terms of the table, we're just starting from the middle and increasing
thanks. I
the
needed to say
spread,
that.
the read.
Yeah, okay, so this is an implementation detail, but I need to explain this for this patch to be clear. What we're doing is we're doing an interpolated table read into this table, which has this strange name to disambiguate it. And the table is defined from, I don't know why, but it's defined from 0 to 256. I don't know why a power of 2, because there's no special reason to use a power of 2 there. So what you want to do is use this, treating this axis as going from -1 to 1. And so to do that, you have to fix it so that 0 goes to the middle. So to do that, you add 129. 129? That sounds I don't know. I worked it out before. I'm not sure why 129, not 128. So add 129, and then it's centered around here, and then multiply by 128 so that it has enough amplitude to get to the edges of the table. And the thing that I better not try to explain is because it's 4-point interpolation, you'd better not give it anything below 1 or above table size -2, because then it won't be able to interpolate. So I actually gave it stuff outside of the range here so that the interpolation algorithm will work correctly. But that only becomes important when you actually implement one of these things. And in fact, if you really were doing this, you probably would use multiplication. You use the multiplier instead of table lookup. And so this wouldn't become an issue. So this is probably, well, my reason for putting this in a table this time was so that it would be easy to switch them and so that you could actually see what functions were being applied. So this is a pedagogical way of doing it, and possibly not really the way you would do it if you were trying to get work done in a hurry. Okay. One other comment. Yeah, just stop looking at that. Yeah, let's stop looking at that. So now, just again about the business about the even and odd harmonics. And I'm going to probably make a confusing job of explaining this, so I'll try to explain it, and then we can have a break, and then I can go back and try to explain it better so it's less confusing the second time around. Let me get that thing back out, because that's actually a good example of evenness and oddness. Sorry, going in circles. Okay, so other thing to notice about these tables is, if this is 0, so now think of this as going from -1 to 1, and so this is what happens to 0. So this one, which is for choosing the second harmonic, is an even function, in the sense that if you give it a negative number, it gives you the same output as if you give it a positive number. Right? The second one is even, the fourth one is even, so it gives you 1 instead of -1, but it still gives you the same thing for positive numbers as it gives you for negative numbers. And similarly, the sixth one, and so on. Any even numbered one of these things is going to be an even function. And there's a bunch of ways of seeing that. Okay, and looking at 3 and 5 now, these are the opposite kind of function, which are odd. So now what happens is, when I put 0 in, I get 0. And if I put something positive, I get whatever I get. But if I put something in negative, I get negative whatever it was going to have been. All right, so to put it another way, is this going to work? Yeah. Okay, so now I have to erase the, woohoo, no, go away. Okay, so now I've saved a copy of that, so now I can say select all, well, do this, select all, backspace, and start over. Okay, I really believe that file exists where I saved that. Oh, if not, I have the screen, oh, are the screensavers working? Yeah, cool, all right. We've got 2 ways of going back to recover that, theoretically. All right. All right, so what I want to do is talk about even and odd functions. So back here, an even function is like this. Well, it's a function so that f of x is equal to f of minus x. And then an odd function has the property that f of x is minus f of minus x. Examples of this are 0. Well, 0 is a stupid example. Let's see. Control Z. Examples of this are 1, that's a function, or x squared, or cosine of x. And an example of an odd function would be x, or x cubed, or sine x. All right. And now it turns out that if you throw a sinusoid through an even function, oh, this is an odd function. If you throw a sinusoid through an even function like this, out come only the even harmonics. And if you throw it through an odd function, out will come odd harmonics. And also, if you look at the Chebyshev polynomials, you'll see that they alternate even and odd. So you get only even harmonics and only odd harmonics and something like that. A way of exploiting this might be the following. Sorry, should I exploit this or should I call a break? I should call a break. Who's got questions about this whole horror show until now? Is everyone completely lost? No. I either see nothing or else I see no, I'm not lost, which means no one's admitting to being lost. Someone ask a question. Oh, let me indulge in a little bit of sabotage. Sorry, sabotage is not really quite the word. Vandalism. What if you just do this? Oh, well, you get stuff. If I want to try to get only even harmonics, I'll try to draw an even function. Sort of even. And here's a sort of odd function. Whoops. And here's nothing. 0 is a perfectly good function, and it shuts stuff up. Right? All right. Oh, right. And while I'm there, how about the Jimi Hendrix function? Whoops, sorry. Let's do it like this. Now I get, I don't know if you regard this as a guitar tone, but now I get distortion, clipping, sort of. That, well, okay, so compare this sound to the sound that I got when I did the nice tame algebraic example. This example, I didn't draw it well enough to be an even or an odd function, although if I did it perfectly, it would be an odd function, wouldn't it? Yeah, sounds odd, right? So now I have something close to a sinusoid until I clip it, and then it starts doing that. Yeah. Okay, next up after that I have to explain what the bias button on the old tube amps does. And yeah, all right, anyway. I did that so that you could think of a nice question to ask me. Yeah.
How do you determine what mixes of multiples of frequencies will show up for indices of under 100?
Ooh. Well, what you do is this. It's not pretty. What you do is you go back to the, can I get, oh, now I'm going to find out if I can read that other. Open. One. Yes. All right. So the basic deal is you get these complexes of harmonics, right? And then what happens is if you took this thing and multiplied it by an amplitude, it would get multiplied by the amplitude. This would get multiplied by the amplitude squared. This would get multiplied by the amplitude cubed, and so on like that. And so what you would get is different mixtures of these things, or the mixture of those things would change according to how the amplitude of the input sound changed.
The proportions stay the same though?
Within this they do, but in fact the change is rather brutal because if you just make this thing louder by 6 dB, this puppy got louder by 24 dB. And that is one of the reasons this doesn't get used a whole lot. Or to put it another way, what happens out... Ooh, didn't do that. That's not a very good access input. Okay, so let's see if I can... yes. Going back to this stuff, what I didn't show you was that this is a 6th degree polynomial. The leading term is x to the 6th. So it's actually tightly coiled inside this square, but as soon as you get outside the square, it's going to blow up very, very quickly. And so as soon as you get past a certain amplitude, the thing will get very, very loud. On the other hand, the thing I vandalized it into, that has the opposite quality, which is no matter how much you push into it, there's a fixed amplitude of output that you can possibly get. Yeah, so it follows that you cannot make a polynomial that does this. Or rather, this is not a polynomial. On the other hand, well, I'll get to that after we take a break. I'll tell you more about how you can think about those functions. So coming up next is bias, which is effectively just sliding yourself left and right in this picture, and also clipping functions under a little bit more control than just trying to draw it with your hand. And there's something else that I have to go find my notes that I have to talk about too. All right, so maybe a 10-minute break-ish. Yeah.
Expected measure of the zero.
Yeah.
Expected measure of the zero of DC or the DC. Yeah. Would it also have a width?
Yes. But it's worse than that because the negative part of the width would fold around to the positive part.
So double, yeah.
So yeah. So depending on how you measure it, sometimes you end up with the DC twice as big. And anyway, it's hard to say which should be regarded as a true amplitude. In other words, if you had a cosine of frequency 0, should you regard that as having the same amplitude as a cosine of frequency 1, or should you regard it as being double because it actually slapped into its negative frequency shadow? And yeah, you'll never see the end of that. That was one of the reasons that I just got rid of DC, was because it's so confusing.
Were you taking care of that?
What?
Where is that being taken care of?
Oh, I think I'm just high passing.
There's a high pass button.
Is there? Yeah.
Yeah.
Yeah, which in fact, if you looked right when I connected it, you saw the DC thing poke up and then back down. That was the 1/5 of a second that it took the filter to get rid of it. Yeah, okay. So I want to talk a little bit more about evenness and oddness. And so there are even and odd functions, and there are also even and odd spectra, and there are relationships between those, which I can sort of explain in the following way. Suppose you had a waveform that looked like this. So I'll draw just one period, and I'm going to make the thing have a pulse in it. In fact, just to make the picture better, I'm going to put the pulse not right at the beginning, but toward the beginning like that. Right? So that's just a pulse. Now suppose that's a repeating waveform. If you wanted only to hear the even harmonics of this thing, what you could do is you could take the thing and add it to its self-delayed 1/2 cycle. If you did that, and if you normalized appropriately, let's see now, how was I going to do this? I guess I can do, okay. Then you would get something like this. Same thing, but you get 1/2 of a positive pulse here, and then 1/2 of a positive pulse a half period later. And if you made that, and if you played that, you would hear something at twice the frequency, because in fact whatever it is actually repeats twice over the length of the segment that I showed you, which was the original period. And you can actually do this. You can, if you want to, you can take any signal that's quite almost periodic, and you can put it in a delay line that is calibrated to be half of the period that you believe the thing has, and add the two and normalize, and then you will get something that's an octave up, if you care. All right, then the other thing that you could do besides add is you could subtract it. And if you did that, you would get something that looked like this. It would have a bump again, but then it would have a bump pointing downward like that. All right? And that signal, if you regarded that as a single period of something that repeated, would have only odd harmonics. So you can think about this and the even harmonics in the following way. The even harmonics are numbers 2, 4, 6, 8, and so on, and those are all multiples of twice the original fundamental frequency. So if you did drop all the odd harmonics out of the sound and left only the even ones, it would be up an octave, which is what you see here. It's harder to understand this as having only odd harmonics, but one way of thinking about that is the following. If I took these two things and added them up, I would get this. Because this pulse would cancel this pulse, and this pulse would add to this pulse. So I get the original signal. So this is the part of the signal that's left after I subtracted out the even harmonics. And so it's the odd harmonics. That's a little bit hand-wavy. That's not really a proof, but that's a way of thinking about it that will at least help you believe it. Another possible way of helping you believe it would be the following. I can draw the first few even and odd harmonics like this. First I'll do an even one. Maybe I should all right. I'm going to be intelligent. This is really dangerous. But I'm going to actually make copies of this. No, not over there. Because I'm going to need a few of these. All right, let's stop there. Okay, so the 0th harmonic looks like this. No, it doesn't. It looks like this, just a constant. First harmonic looks like this. Second harmonic, what did I do wrong? Second harmonic has a full cycle here, and then another cycle there. Bad, drawing bad. And then it goes down and then up, like that. And then this one goes, let's see, I got to get 3 cycles in there, so it goes cycle and a half, cycle and a half, like that. And this one I'm scared to even try. I get
It's the same one we had before.
this one?
Yeah, it's the
No,
same
because
one.
this is
The
positive.
one
And
to
this
the
is,
right.
Yeah.
oh, what did I do wrong? These are the, oh, this one is dead wrong. That one I did something terrible to. Let's go back. Yes, it's working. Okay, so so this is now harmonic number 2. I need harmonic number 3, which will go 1.5 cycles, cycle and a half, and then 1.5 cycles. That would be 3 cycles. Yeah, right. Yeah, it has to be. Oh, this one's
Well,
wrong.
That one doesn't have enough. Right?
This one's wrong. All right. Sorry. Lose it. And go back. Now I'm going to try to draw. I don't know why I'm doing this. I'm not going to draw them well enough that you'll actually see the point anyway. I'll get 2 cycles in the first half. Cycle, cycle. And 2 cycles in the second half. Like that. All right? Okay. So the thing that I want you to notice, I'm not even going to try for the next one. The thing I want you to notice is that these are all symmetric about the middle of the cycle. These are anti-symmetric about the middle in the... What? What have I done wrong? Oh, I'm telling you just, what I'm telling you is dead wrong. That was just the wrong thing to say. These things have the property that the first half is the same as the second half. In other words, here you get nothing, no change, and then you get no change again. Here you get a full cycle over half a period and then another whole cycle. Here, you get a half cycle, and then you get the same thing repeated, but the thing that got repeated is out of phase with the first half. And here, too, you got a cycle and a half, so that it got down to -1, and then goes from -1, it's the same thing backwards to get from -1 to 1 as it was to get from 1 to -1. So the odd-numbered harmonics, the odd-numbered sinusoids, so harmonics number 1, 3, 5, and so on, all have the same property as this, which is that the first half of it is the negative of the second half. The thing about mirror symmetry is something else. That's whether the thing has the phase of a cosine or of a sine. And I want to not get into that just yet. All right? So these things are even harmonics which look like something that's repeating twice as fast, and these things are odd harmonics which looks like things that are repeating twice as fast, except the second time it's upside down. All right. Okay, the reason I was doing that is suppose you took a sinusoid which has, well, the first harmonic like this, and suppose you then put that into an even function. In other words, now what we're going to do is we're going to take this thing and do something like square it, which has the property that if it's negative, it squares to the same thing as if it's positive. Okay, so recall that the second half is actually the negative of the first half. Well, that means that if you apply an even function, you get the same thing in the second half as you got in the first half, because it was negative, but the even function treats the negative as the same as the positive. If you took this and threw it to an odd function, then the second half, which is the negative of the first half, then turns into something that is the negative of the first half again. And therefore you get a thing which has odd harmonics in it.
Can you say that last part again?
Yeah. Okay. So the odd function applied to this waveform does the following. If you put something negative in, you get the negative out. So if the second half of the thing is the negative of the first half, if the second half of the cycle is the negative of the first half, then what comes out will still have the second half of the cycle be the negative of the first half of the cycle. And so in general, it will be a thing which is of this form, which is an odd harmonic only sound. Confusion. I'm not trying to confuse you, but even and odd functions are not the same thing as even and odd harmonics, even though they sound like it. If you have a sound that has even and odd harmonics, that does not actually correspond to an even or odd waveform as a function. An even waveform function is, well, okay, let's just look at the first harmonic here. This is cosine. Let's go get sine now. The sine looks like this. Still drawing. But let me not do it there. Let me just do it somewhere else. So let's move this over. So now let me just try to draw the same frequency but a different phase. Whoa, not that. Please give me this. Sorry, bad drawing. Okay, so this is the same frequency as that, and the only difference between those two is the difference of phase, right? Okay, this is if you regard this as 0, you could put 0 anywhere in this period that you wanted to for practical purposes. If you think 0 is in the middle of this thing, then this is an even function and this is an odd function. But they are both an odd harmonic. So even an odd function does not mean even an odd harmonic in that sense. If you think of the harmonic itself as a function, it's not even and odd depending on whether the harmonic is an even and odd number. That's a different thing. And there, evenness and oddness is whether you have a sine or a cosine phase in that partial. All right. So I'm just telling you this so that you can remember that this is confusing, and that you will get bollocksed up about this at some point or another in your lives, I'm sure, because I do. All right. So that's evenness and oddness. Now, evenness and oddness in practice, well, part of it was this thing. While I'm here, I'm forgetting to do something, which is, so here's the 6th power. No, that's the 6th power. I should show you the graph of that because it's entertainingly different from what happened when you squared it. So now what you're looking at here is the original sound and the thing squared. And now if I graph the original thing and the thing to the 6th power.
You didn't do the original.
Ooh, thank you. What did I do wrong? Scope. Wow. I want scope 1 to be the original. And scope 2 to be the result, right? Yeah, okay, so that's what went in. And now what comes out looks a little bit like the 2nd power, except that it's squashed more. Okay, why did it get squashed more? Well, one way of thinking about it is these numbers are all between 0 and 1. And if you take a number between 0 and 1 and square it, it gets smaller. If you raise it to the 6th power, it gets smaller yet. So what happens is the numbers which weren't, 1 is always going to be 1, but numbers that aren't quite 1 are going to get squashed progressively harder and harder towards 0, so that what we'll see is a train of pulses, but the pulses will get narrower and narrower as the power goes up that we apply. So if you want to, you can think of this as a kind of pulse width modulation. There's going to be a problem. You're going to want to do something smarter than this to actually do pulse width modulation, because this doesn't work correctly for powers that are not integers. So we'll have to go a little bit further before we can really get that going. But one way of thinking about these timbres is that's a fat, here's the original sound. Here's a kind of fat pulse, and here's a skinnier pulse. And if I made that pulse much skinnier, it would have a brighter spectrum.
You have to compensate the frequencies of those too?
No,
it's
but
narrower,
what happens is the power goes down. And something wonderful happens about that, which is psychoacoustic. The bandwidth, you can forget I said this. The bandwidth is is proportional to 1 over the peak width of the pulse. So if you got a pulse width that's smaller, the bandwidth gets louder, or gets larger, which means you get more and more partials. So what happens here is that the total power goes down, but as the bandwidth is going up, the number of partials is going up. And because of psychoacoustics, you actually hear that as a louder tone. So you actually don't, at least for the first while, you don't actually really hear a diminution in loudness as you squeeze the pulse. But if you carry it to an extreme and drop the pulse down to like 1/100th of the width of the period, then suddenly you notice that the power really did go down. Or sorry, the loudness really went down. I'll demonstrate that when I actually make a controllable pulse width thing, which is on my list, although I might not get to it today. What I want to do first is show you the tragic consequences of even and odd functions as wave shaping functions in more detail than this. So what I'm going to do is get rid of this. Well, not get rid of it. I'm going to save it and then make another one. And I think I'm going to call this Trig because, I don't know, how about sine and cosine? Okay. So it may have occurred to you, as it occurred to a lot of people in the 70s, why don't we just try the sine and cosine functions as wave shapers, because they're nice trig functions. They should give you nice spectra in some hazy way of thinking. And the answer is that they do, and the result is rather entertaining. So I'm going to make the result by, let's get rid of this. I'm going to keep the scope stuff. Get rid of Chebyshev polynomial. I'm going to get rid of this. I want now, for reasons that will become clear later, I want a controllable amplitude here. So what I need to do is now get a number. Let's give it a reasonable range divided by 100, pack 0, 20, line tilde. Boom. Right. This is now a smoothly changing function which goes from, whoa, not there, here. This is a smoothly changing function, or what do we say, smoothly changing control which goes from 0 to 2 in value. Because I took this thing, which is a reasonable thing in pixels, and divided by 100. Right? Why 2? I'm not sure, because 1 is full blast, and I'm going to want to get louder than full blast eventually. All right. Now what I'm going to do is try a nice trigonometric function, like cosine, and see what that does as a wave shaper. So once again, I'm going to want to be able to hear the original sound. And I'm going to want to be able to hear this. All right. Hey. Oh, yeah, absolutely, but I don't want to close it. All right, so original sound and this sound. Of course, if I multiply it by nothing, it's nothing, and so it's nothing. Now if I give it some juice. Okay, now cosine, recall, is an even function. It's this function here, if you like. I'm being a little bit sloppy because really this is 0 here if this is cosine. And so you have to believe it's still an even function around this point, because if you look at it over here, it's still the mirror image of what it is over here. So cosine is nice and even, and of course, like any proper even function, it took the original, which is that, and it knocked it up an octave, put it up an octave, right? Now, what about sine? Well, this is embarrassing. PD doesn't actually give you a nice sine. Instead, if you want the sine of something, this I think my reasoning for this was that you actually always should be using cosine anyway. If you want sine, you should just subtract a quarter wave from it and take the cosine. The practical reason is because that way you only have to use one wave table, and so you get better cache statistics, so it'll run faster. And speed is everything in computer music. All right. And of course, cosine is a nice even function, sine is an odd function, and so we will hear thing down an octave, odd harmonics only, right? Now, those of you who have ever used a Buchla synthesizer know that it's really cool to have a whammy bar that changes you between even and odd harmonics. This is true not only for, say, square wave / sawtooth oscillator things, it's also true for this kind of thing where, all right, so here I don't do anything and I get even, here I subtract a quarter and I get odd, so I could subtract a controllable amount and get either even or odd depending on how I feel. And that works like this. So I'm going to subtract all right, but I'm just going to subtract some number which I will have range from 0 to 1/4. So the control control will go up to 100. And I'm going to do, so I want it to go up to a quarter, so I'm going to divide by 400. Right, and now I'm going to subtract that from my sinusoid, take the cosine, so that if it's zero, there's nothing happening and it's cosine. If it's a quarter cycle, then we're subtracting a quarter, so I'll put 100 here, and I get the sine, and anywhere in between, I have a continuous control between the odd and even harmonics. All right? Questions about that? So in computer music, if you ever just need a test tone that has harmonics in it, do this. Take an oscillator. Take an oscillator, subtract or add. It doesn't actually matter. Just to be consistent, I'll subtract. Subtract something between a half and a quarter. Then take the cosine of that. And then listen to it. And you've got test tone. And if you want the test tone in 3 objects, and if you want a softer timbre, which I usually do, then just drop this number down a little bit. Oh, I need to explain that, but do this. Multiply it by 1/3, and then you'll get this. All right. Now, what? Oh, yes, right. So I have to go back and say something more that I forgot to say earlier. Going back to this example here. Okay. So here we have. Here we have a thing which can be even or odd. There's another control, and so maybe this is about halfway between. It's not really accurate. There's this other control, which is how loud the signal is that you put into the nonlinear function. Right? Now, I'll just show you. It's the same effect. Get some more room. It's the same effect, roughly speaking, as I got with the Chebyshev polynomials. Oh, and I probably got rid of that, didn't I? No, I didn't. Oh, except, yeah. Okay, so here, let's shut this up. Right, so here again, there was this thing where you could control what I was calling the index here and get these timbres out. And this is exactly the same operation. And those of you who've been around 80s synthesizers recognize this sound, because that's the sound of FM when someone gets out of control with the index knob. Right? In particular, what you hear, I can show you, let me show you what you're hearing, if I can. Let's see, do I have the spectrum still? Yeah. All right, so what I'm going to do is I'm going to send to something bad is going to happen. Maybe not. Oh, the send is right here. Hey, look, I can just do this. Okay, so let's see what we're making. Oh, and by the way, here for Isaac, here's what happens when. Oops. Here's what happens when you. This is putting out DC right now, and so if you look at DC, it says, "Oops, yes, no," for a second, and then the filter saves us. But anyway, so now changing the loudness of what you put in does this. Okay, now those of you who studied Computer Music 101 probably recognize that that's what FM does when you bang on the index. And there's actually a reason for that, which is that this operation is a mathematical close relative to frequency modulation. So just to avoid any malpractice suits, I'll just tell you what the relationship is, and then we can just sort of know that it's there and forget about it for later. The relationship is this. I'm sorry, I have a philosophical question of whether I should start a new blackboard when I change a topic. Let me see if I can fit on the same blackboard, because the fewer pages of blackboardy stuff, the better. All right, so here's what I'm going to claim. What is FM? FM is usually implemented as phase modulation, and so I'll write it down as if it was phase modulation, and it's something like this. It is a signal, so I'll just give it a name, X in. Oh, let's just say this is FM. Okay, here's the signal. The signal is the cosine. You could say sine or cosine depending on what phase you want to be talking about, but I'll say cosine for now. And now what we're going to do is we're going to have a carrier signal. So we're going to say cosine omega n, but instead of just closing the parenthesis and making a sinusoid, we're going to add an index k times another sinusoid which has a different frequency. Usually people say this is the carrier frequency, and this is going to be a modulator frequency. Ooh, modulator. Now I've got to close the first paren. Okay, so cosine of omega carrier times n. N is the number of the sample, so it's just time. And then we're going to add another cosine into the phase of the first cosine. And now the cosine sum formula comes out. This is not the fundamental formula for computer music, although they follow from each other very quickly. So this is actually equal to the cosine of the product of the two cosines. Cosine of k, cosine of omega modulating frequency n, plus, plus, and now I got to start on another line, and anyway, it's not plus, it's minus the product of the sines. Right? Okay, so this is a direct application of the formula that the cosine of A plus B is the cosine A cosine B minus sine A sine B. Right? Now each of these, this I'll talk about in a second. This is exactly that's exactly what I'm doing here. Almost. Actually, it's exactly what I'm doing here. Specifically, I'm taking the cosine of omega n, I'm multiplying it by k, an index, and that's, by the way, why one uses the name index for this amplitude or this gain that we apply here. Okay? So we'll adjust the amplitude of this cosine by this index. This is, by the way, going to be the modulating frequency. And then we're going to take the cosine of that, and then all we would have to do to get the FM spectrum is we would have to then ring modulate that by another sinusoid whose frequency was the carrier frequency. So this here is a harmonic sound whose fundamental this is a harmonic sound whose fundamental frequency is twice omega m, because this is an even function. So it doubled the frequency. And this is omega c, so the component frequencies there are going to be multiples of 2 omega m plus or minus omega c. These are going to be odd multiples of omega m plus or minus omega c. And so that this and this are different harmonics, but if you put them all together, you get all the harmonics, which are omega multiple of omega n plus or minus omega c. Or, and then since cosine is the same as cosine of its inverse, you can also write that down as all of the omega c plus or minus all of the multiples of omega n. And those are the frequencies that are present in FM, and that's why FM has the spectrum that it has. Furthermore, if you studied engineering calculus, which I skipped, you would recognize here that the spectrum of this thing has amplitudes which are given by Bessel functions of the whichever kind they are, but the J Bessel functions. And you can carry out a wonderful thought experiment wherein you take a microphone and swing it around your head as a nice sinusoidal wave passes over your head. And this makes FM because of Doppler, and you can actually use that trajectory to understand why the Bessel functions are in the spectrum of FM. So that's, for those of you who are mathematically inclined, see if you can work that thought experiment through and make it work. And then you don't have to learn your Bessel integrals, you can just do the whole thing by thought experiment. Yep. Okay, so that was not exactly an aside. That was me telling you that we're not going to do FM here because, in fact, FM is subsumed in this beautiful general theory that we're now creating, which just explains everything, and FM just happens to be a side trail. Even though, of course, FM is the thing which drives the entire money scene for computer music. I should say that even though these expressions are the same, this expression is a faster one to compute than this one, obviously. And so this is the way you actually do it. And another thing about this expression, but in fact also about this, is that if you think about cosine as a function to wave shape with, it gets away from a bad property that those polynomials had. So let's get the polynomials back. Where are the polynomials? Here. So the polynomials all blow up as you get outside of a fixed range. Cosine doesn't. Cosine, the further out you get, the more it just wiggles back and forth. So the amplitude is actually very well determined when you take, when you throw almost any value that you want into a cosine, you know that the result's going to be between -1 and 1. That's a really good thing for audio engineering because you know pretty much for a fact what the amplitudes are going to be that come out of the operation. That's not going to be true of doing wave shaping like this, but in fact it would be true in general of any kind of wave shaping function which was bounded. And so cosine is bounded because it just looks like this forever, but for instance the clipping function, or a clipping function like that, also is bounded if you allow that it levels off as you give it very high voltages in positive or negative. And this is why circuitry, when you use circuitry to do distortion, it doesn't blow your ears out the way the Chebyshev functions would. It's because, in fact, real circuitry always saturates, and so there's always some voltage at which it actually will behave like that, which might even just be the limits of the power supply voltage of your amplifier. But those limits will be there somewhere. Okay. Questions about this? Yeah.
I think it might help illustrate the comparison. Maybe if you could translate the PD wave shaping to like the symbolic representation.
You mean which? You mean this one, or you mean?
No, in sine and cos 3.
Oh, this one. Oh, yeah, right. Okay. Yeah, that's a good idea. Let's see if I can squeeze it down here. Bad habit to try to squeeze stuff on the end of your blackboard. But let's do it. So what I'll do is I'll just say divider. And anyway, that thing is something like this, wave shaping. Oh, actually, that's not the right thing to say. What I should say is 3 dot sine and cosine dot PD did this. There what we did was we said cosine, okay, so the expression goes from the outside in, so it's cosine of, and now we're going to subtract something, so I'll put this in first and then subtract that. So this is now going to be an index times cosine of, and fill in omega to be correct for getting a frequency of 220, right? So omega in, and then we're going to subtract this thing, which is an offset. I think I should use the letter phi for that. Sorry about using Greek, but usually people use phi for things like this. Because it's a phase shift on this cosine, although psychologically maybe you shouldn't think of it that way. So then what you can say, if you want to, is now we could go back and apply the formula for the cosine of the sum of two things, and you would see that this is actually a linear combination, depending on phi, of the cosine of k cosine omega n and the sine of k cosine omega n. The cosine gives you the even harmonics, and the sine gives you the odd harmonics, and this theta magically controls which of the even, or the weight of the even and oddness that comes out. All right. Okay, so there are two other examples of wave shaping functions to know about. Maybe more than two, but two that are truly fundamental. One is just throwing the thing into an exponential, and the other is throwing the thing into, well, inventing good saturating functions. And what I'm going to do first is the exponential function, because actually there's no good order to do them, and it doesn't matter which you do first, I don't think. Okay, so right, so what I should do is, no, nothing. I'll just hang on to this. But as soon as I need to make more equations, I'll just start a new blackboard. But that's all right. Okay. So now I'm going to save this and now prepare to do exponentiation. All right, so that means do a save as. Oh, actually, let me do something else. Before I do that, let me show you where to get this in the PD help, because that's where it's nice and explained. Exponential. Okay. So this now is in the PD help browser. And this is a thing which you will see do something like what happened to the powers, except not exactly. So let's see. Why don't you just tell it to start graphing repeatedly. Now here I made some kind of decision about how to deal with DC so that I could actually show DC. And I can't remember whether I counted DC for twice the power of the cosine or not. I believe that's what I did. So that here's an amplitude of 1. I believe this is the just 1. But cosine of omega t will show up with an amplitude of 1/2. And for more about that, wait a year and see what I do next winter if I hold plans, and I will actually talk about frequency domain and give you a clear explanation if you stick around for why that would be true, if I can think of a clear explanation. All right, so here, what's happening now is we have a function which is e to the minus, I'm going to need to get another blackboard out. This is a falling exponential. So what that is what happens if you put money in the bank and time goes backwards. Or something like that. Or another thing about this is what happens when you put an impulse into a simple low-pass filter. So there are lots of things that might give you this. It's also how much radiation is in Madame Marie Curie's body as time goes on, that kind of thing. All right. Okay, so now what we're going to do is we're going to take fundamental frequency. This is, in this patch, the fundamental is chosen specifically to make the spectrum easy to graph. And hand waving, I'll just wave my hands over that. So the fundamental is fixed, and here's an index, again, which is a thing which you take and multiply by the sinusoid. But here there's a twist, which is the following. And here I need to get a blackboard out to show you why you have to make a twist. So I guess what I'm going to do is now save a copy of this.
You know that the page there that you're drawing on is actually bigger than what you see on the screen.
Oh.
If you wanted, you could also just scroll down.
Oh boy.
if you
Yeah.
wanted things to all be on one document.
Yeah. I'm afraid I might actually get myself fatally mixed up if I did that. So, and anyway, this really is a new topic. All right, so we'll do this. But thank you. What I'll do is I'll resize them so they're actually the size of the screen in the future. Okay, so I'm going to save that. I think that's good. And then just to show off, let's go do this. Oh, no. Ta-da. All right. Tight security there. All right, what are we doing? We're going back and we're saying, okay, we just saved a copy of this, so now I can do my wonderful select all and backspace. And now, all right, so exponential function. It looks like this. Okay. Whatever the horizontal axis is, the exponential function does something like this to it. Except actually, well, all right, that's good enough. So 0 is a place where the exponential function gives you 1. So if this is 0, this is 1. This is anything at all, and this is the exponential of x, or as mathematicians would call it, e to the x. Oops, except that's a bad e. Like that. This is how you would invoke it in a function and another way of writing it. Okay. Now, thinking about this as a wave shaping function, picture of wave shaping, a picture of wave shaping might be you put the, you use the sinusoid that you're putting in. By the way, it doesn't have to be a sinusoid. We're just doing sinusoids to be simple right now, except for that one time when I actually threw the guitar through it and it got complicated. But sinusoids, it's been sinusoids for the rest of the evening, right? Okay, so you're putting a sinusoid in, it goes positive and negative, and you think of that as moving along the horizontal axis. And in the stuff that I've shown you so far, including the Chebyshev functions, there was a sort of a natural range from -1 to 1. Here, there's no natural range, and in fact, the louder the sinusoid is going in, the louder it is coming out, potentially catastrophically, because, of course, this is an exponential function, which means every time you just add 1 to the amplitude, you perhaps double, or in fact multiply by e, the amplitude going out. By the way, I'm saying e to the x instead of 2 to the x here because the Taylor series is simpler. That's one reason to say why I would use e. The math will be yuckier at the outset, but will be simpler later. All right. So it would be a very bad thing to just take this and plunk it into the diagram that we had before, which is, make a sinusoid, multiply it by something, and then run it through the wave shaper. Because, you could change the timbre, but you would change the loudness a whole lot more than you were changing the timbre. And maybe you wouldn't want that. Well, okay, so what you can do then is you can just normalize it so that the furthest the sinusoid gets over to the right, which is the higher the function gets, should correspond to a height of 1. In other words, what I'm going to do is I'm going to not make a wave shaper that just gets louder as the thing goes out, but I'll fix it so that the bigger the sinusoid that goes in, the more I'll drop the exponential so that it only reaches 1 wherever the sinusoid takes me out. I'll just re-normalize or rescale the exponential to be correct. Well, it turns out that there's a conceptually simple way to do that, which is rather than make the sinusoid be centered around 0, make the sinusoid only reach up to 0. So if I draw the sinusoid, this way, don't do this, but rather, okay, how about, I'll just say no. Rather, do this. All right. In other words, fix it so that no matter what amplitude you give the sinusoid that you're going to look into the nonlinear function, it only reaches up to 0, and therefore the output only reaches up to 1. All right. This patch does that backwards because this is an exponential function thrown around backwards. Also, this has some normalization or another, and I'm not actually sure how it's normalized, so I don't know whether it's e to the x or 2 to the x or something else to the x. It's whatever. But it doesn't actually turn out to matter in what comes out. What does come out is the following. If I take this thing and put a sinusoid in, because this is flipped around backwards, the sinusoid now should be adjusted so that it's always positive. Then what will happen is when the thing hits 0, this thing will hit its maximum, which is a value of 1 coming out. And when it's something else, it'll be something smaller than 1. And therefore, I'll have a nice controllable amplitude, but I'll be using an exponential. Okay. Why would someone think of using an exponential? Well, it's because exponentials are the same functions as sines and cosines viewed differently. And I'll give you more about that later if I can't avoid it. But if you're trying sines and cosines, then a physicist or a mathematician would immediately say, well, those are just complicated ways of using exponentials. Why don't you just really use an exponential? And the answer is, okay, I'll try an exponential and see what happens. The math will be simpler, and therefore I might actually come up with something that I can explain, as opposed to those horrible Bessel functions. Well, it's not going to be that good, but it'll be a little bit better than those horrible Bessel functions because, well, you'll see. All right. So what comes out then has a waveform, which is getting graphed here, and has a spectrum, which is getting shown there. And of course, if the index is nothing, all right, so we're taking the fundamental, we're driving an oscillator with it, and then we're adding 1. What that means is that we're making a waveform that ranges from 0 to 2 in value. And then if we adjust the amplitude of that, it'll range from 0 to something, which can be 0 or can be 100, whatever we want. Right. So to do that, we make an index up. I think this is going to range from 0 to 100 or something. Oh, yeah. Anyway, it's got a reasonable range. It's got a fair amount of kick to it. And then we'll multiply this thing by something that will vary, well, if this is 10, this will be 1, and that'll go up to 2, and we'll get up to about here in this table. All right, and now let's see if we can hear it. Oh, we can't because the index is 0, so right now it's getting multiplied by 0, so we're just reading this value of the table, which is giving us nothing. So instead of doing that, let me give it some index so that we can see what's going on. And now we can listen to it. Now okay, so turning the index off to nothing gives me nothing. And in fact, now we see what the signal really was. The signal is just 1 if I give myself 0 here. So if I give myself something really close to 0, you'll see it. Right, 1. Okay, and then if I give it if I give it some amplitude, then what will happen is the sinusoid that I'm using to read this function reaches further and further here, and so the thing gets lower and lower at its bottom point. Never actually gets all the way down to 0. But it gets very small, and the proportion of time at which it's at which it's close to this point gets smaller and smaller. So this is a way of doing pulse width modulation. And furthermore, it sounds like pulse width modulation, sort of. The respect in which it doesn't sound like pulse width modulation is that classical pulse width modulation is done with rectangular pulses. And the spectrum of rectangular pulses is much more complicated, but there are occasionally partials that drop out. Right? So that, for instance, if you have a pulse that's 1/3 of a cycle, there's no third harmonic in that pulse. And things like that happen. And here, if you look at the spectrum, there's none of that sort of going in and out of partials. The spectrum simply widens or fattens as the index goes up. So the spectrum starts out being the spectrum of 1, which is all DC. And as the index goes up, more and more energy goes from this to higher ones, but it maintains the property that the loudest partial is always the 0 frequency 1, and the partials all drop off in strength monotonically. That's to say, it's decreasing. It doesn't go down and up. It just goes down. So if you like, it's a nice bell curve, although it's not. And in fact, the bad news is that they're Bessel functions. They're I Bessel functions instead of J Bessel functions. but they look a lot neater than the J decimal functions, and you can think about them much more simply because you can actually predict this bandwidth, which is actually 1 over this pulse width, and the pulse width you can figure out by figuring out what portion of time the cosine spinning is reading, which is a decreasing function of the index. So you get this kind of action. And notice, and this is just psychoacoustics, that the thing doesn't get quieter even as the average power is going down because the power is being distributed over more and more partials as you push the index up.
Where is our read point centered on this graph?
It's
starting at 0?
Starting at 0 and reading positively. Yeah.
Then I would imagine we would see more discontinuities like in the part before it really starts to sharply.
You mean this part?
Yeah, like say it's only reading over to, say, 1 or half or something like that. I feel like, I know it's a sinusoidal read, but still I would feel like it would get like much sharper discontinuities.
Yeah, I guess what's happening is it's just wiggling in a very small region here, and even though the curve is very sharp, it's not very nonlinear. It's just got a lot of gain.
Oh, okay, right. So a lot of that is just coming from the read shape that we're seeing. Okay.
And all the curvature is happening down here.
I was looking at it the wrong way.
Yeah. And that's a figurative way of talking about it. It's not really curvature, but who knows. Anyway, something like that's going on. All right. And this is a good thing because you can now, well, first off, this is a good way of generating a pulse train that has a nice controllable spectrum. The gotcha is that it's not band limited, so at some point you're going to hear fold over, although you really have to punish it before you get fold over. So just to punish it, let's see. There's a lot. Well, I'm cheating a little bit because this fundamental is actually a subharmonic of the sample rate, so this will work well. But you get about to here before you start getting appreciable fold over. Right. So this is actually a good starting point for subtractive synthesis if you're doing digital subtractive synthesis, which it sometimes is hard to do using the classic analog waveforms because it's hard to band limit them. This is a thing which gets around that. Also, while we're here, this is just a thing to mention that might become interesting later. You can take this thing and move the spectral center around. And the way you do that is by the time-honored technique of ring modulation. So if I took the fundamental again and I multiplied it by something, this is an aside. If I multiply this by some nice integer and make that be an oscillator, and then multiply that oscillator by the result of this process, got no change so far because this is 0, but if I start giving this some frequency like this, nothing happens. What have I done wrong? Oh, this fundamental is not a signal. I have to get in here. There's the fundamental. I have to click that. There we go. Sorry, I'm cheating a little bit. So now I'm ring modulating by a sinusoid of triple the fundamental frequency, and I'm getting something that is centered around harmonic 3. And this is now a way of generating formants. This is closely related to, but not exactly the same thing as the Pof, the phase line formant generator. And I think I'm going to avoid going full scale into that because that's pretty well written up. And what I'm trying to do is tell you all the stuff that you can't get in the books. Okay. Questions about what I just did here? So if you want more about this, go into chapter 6 of my book, and the whole thing gets spread out in gory detail later. But this is just to tell you that that's there. Oh, right. And now that I've centered around 3, I can still change the index, which is now a bandwidth control. Right. So that can be a powerful general synthesis tool for making harmonic spectra. Harmonic spectra are dull, but if you want to make harmonic spectra, this is a powerful way to do it. Oh, by the way, if you didn't, you would change this to something other than an integer, and then you get an inharmonic spectrum, like this. How about 3 and a 3.2-ish? And now I do this, and I get a finish sound. And that's, we all know about that. It's all the same stuff. Everything in all that, what did we call it? All that unit generator based oscillators, modulating oscillator stuff that everyone was doing in the 70s basically amounts to ring modulating nonlinear distortion products of sinusoids. If you want to understand it that way. It's not the only way you could understand it. Questions about this? Before I jump topic altogether and start talking about clipping a little bit more. Okay, clipping, saturation, right? Which is, of course, the real reason that we know about distortions, because it was discovered, I'm not exactly sure by whom, but maybe by some guitarist who discovered that they could make their amplifier malfunction and it sounded better than when their amplifier was functioning correctly. And the way you do that is something like this. Oh, should I save this? I don't know. I guess it would be a good thing if I did. Ugh. Yuck. 206. No. Files 1. So this is going to be 4, and it's going to be. I guess I want a dot there to be. Okay. So this is very closely based on the thing that's just in the PD thing, but I couldn't resist adding this ring modulator. Okay. Let's close that. All right. So that's about using an exponential. And now the only thing that's left is talking about saturation, which I will now try to draw a picture about. I'm saving saturation for last because although it's simple, it's actually very hard to make it sound good. And I'm not really making it sound very good in the examples that I'm trying to make, so I'm a little embarrassed about it. But and I'll tell you why, but I'll try first to describe it. Okay. So saturation is just taking a sound and putting it through a function that either could be just a bunch of line segments like that, or alternatively could be a function which is rounded. Like that. And both of these things just go forever. So they all presumably have asymptotes limiting amounts they hit, both positive and negative. Right? Now the idea, as usual, is you put whatever signal you want on the horizontal axis, and then this thing reads it. This thing here, the one that consists of segments, is a clipping function. You can regard this as being the output is equal to the input on this range, and then the output is its maximum here and its minimum there. And that's actually done in a PD object called clip tilde. Unfortunately, that's not actually that's not the best sounding clipping function, even though it calls itself clip. And nobody actually knows what the best sounding clipping function is. I thought I knew until this afternoon when I decided to make a demonstration of how bad the bad clipping functions are and how good the good clipping functions are, and I got results that contradicted what I thought the truth should be. So I'm going to go back and think some more about that. But at any rate, there must be some clipping function in the sky, which is the ultimate clipping function for putting sounds in. It'd give you that nice warm fuzz without the shrill, buzzy stuff. Okay, shrill buzzy stuff you get, as you might imagine, by having corners in the function, which is like what happens when you turn a transistor radio up too high. And the nice soft rollover thing is like maybe what you get with tubes, although actually if you look at what a tube does, it clips really hard. So something about that mythology about tubes is wrong, and nobody knows what this thing about tubes really is now. And so if you want to make money in this field, go make a modeling amplifier and go try to persuade someone that you can model tubes, because no one really seems to be able to. And so every year there's a thing that sounds exactly like tubes. And it's an endless stream of money. And there's an endless stream of 13-year-old male electric guitarists who just want that tube sound, and their parents will pay for it. So that is bread and butter. Just saying. All right. Okay, so now let's just do it. In fact, just to be cruel to myself, let's do it to the guitar sound. So I'm going to do a save as here, and we're going to go up to 5 and do clipping. I want to show you clipping because I'm pretty sure that clipping is going to sound lousy no matter whether I can get another thing to sound good. Okay, so clipping is done this way. So first off, I want to get my nice looper out. Oh, actually, let's do it with the oscillator first, because that will be, what's the right word? Pedagogically useful. Okay, so we're going to do the same stuff, which is to say we're going to have an oscillator with a controllable amplitude, and then we're going to add a bias to it. And now it's going to be called bias because that's the name of the knob on the tube amp. Right? And now instead of saying cosine, we're just going to say clip. And you have to tell PD what you're going to clip from. So I'm going to clip between -1 and 1. Well, why not? I could have chosen different limits, but that's the simplest possible choice I could have made. Let's get rid of that. I don't know. Maybe we're going to want the spectrum. Okay. So we're just messing with an oscillator so far. And let's see. I got to give it some amplitude. And yeah, where's the spectrum? Wrong button. No. Wow. Yeah, I think that's. I don't know. All right. Never mind that. Okay. We're looking at the spectrum of a sinusoid. All very good. That's going to continue to look like a sinusoid until I make the thing clip. Because what's happening when I have a low amplitude is it's going to be in the straight region of this function and is not going to clip. And as soon as I push 100 here, well, actually, let's get rid of bias. As soon as this thing hits 100, then we're going to get stuff. Now, notice what happens here. This is different from, turn this down. This looks and sounds different from what I got when I did the pulse width modulation. There I got this nice, orderly increase in bandwidth that was basically, the spectrum has got wider and narrower. Here what happens is the spectrum is nothing until it is almost immediately infinitely wide. So now I'm just clipping a little bit. Can't even hear it clipping yet. Oh yeah, there it is. And what I got is everybody's in there. Oh, actually not everybody. All the odd harmonics are in there. Because this is an odd function and I'm putting an oscillator in. And then as I push it past the safety zone, I just get junk. Which is to say I get stuff that goes off as roughly 1 over frequency squared for technical reasons. And it goes up. I mean, you get this sort of triangle wave sound, right? Okay, if I push this, and this is actually safe, so I'm going to do this. I'm going to now give it 1,000,000. Well, the thing is, this thing never got past 1. Don't do this. Don't just type 1,000,000 into a number box when you've got speakers that big. No. In fact, okay, so what I'm doing now is I'm making a comparator or a square wave generator, which is to say, this, as soon as the sinusoid gets the least bit negative, like more than 1,000,000th negative, it's going to clip to -1. As soon as it gets more than 1,000,000th positive, it'll clip to +1. Oh, let's graph it. What? Well, I didn't hook it up. Yeah, there it is. Oh, it's not graphing terribly well because it's aliasing graphics here. But at any rate, you can see it's positive, negative, positive, negative. It's a square wave. That's cool. Now, how would I set about making it be a rectangle wave instead of a square wave? Close. What I would do, okay, so here's the picture. So what's happening is I'm giving it a very high amplitude sinusoid so that it's negative here and it's positive there. If I took that sinusoid and just slid it over, then it would spin less of its time negative and more of its time positive. So what I can do is I can just, that's why I put the bias in. Oh, except I really should have put the bias in before I multiplied by 1,000,000, shouldn't I have? Because I'll have to make a lot of bias here. But I'll just multiply the bias by 1,000,000, whatever. And now I can slide the sinusoid around. Whoops. Well, that's a little bit too much, isn't it? How about let's multiply it by, okay. First off, I need to be able to use negative numbers here. And second off, that seemed to be an unfortunate choice of range. Don't know why, but I'm not going to ask why, I'm just going to fix it. All right, there it is. So this is a sound that you all recognize from analog days, right, as being pulse width modulation. And if I graph it, let's get up there and then graph it, you'll see that it's like the original thing except that it's spinning a tiny fraction of the time up there and a big fraction of the time down there. Okay? And the reason for that is because the thing that I'm doing over here is changing between a sinusoid like this. Oh, sorry. Changing from a sinusoid like this is not drawn to scale, to a sinusoid that's just slid over. Which is, and this adding there is the same thing as adding a number here. All right, and I should get to a nice stopping point, but I'm not going to be able to, so I think I should just stop. The next thing to ask about is what happens when you round it. And the answer, well, or to put it another way, how can you get rid of that buzzy stuff? And that buzzy stuff is okay for this nice low tone, but if I gave this something a couple of octaves up, then you would start hearing major foldover and other bad timbral stuff. So you would want to be able to not have this thing be so sharp.
Well, we're already hearing some.
Probably, yeah. Although I'm close to a subharmonic of the sample rate, which is 44K1. So I'm cheating a little bit. Yeah. And who knows whether they decided on 44.1 because it would make a beat when it filled it over. Don't know.
Something.
All right. This is a place to stop for now.
What was your inclination for the godly transfer function?
Well, all right. So there's sort of two classes of them. One is you fit a polynomial. You just make a polynomial that gets you from -1 to 1, and you could do a cubic or a fifth order or fifth degree or seventh. And then after that, you should probably stop trying to gild the lily. And the other thing that you could do is use another transcendental function, and the ones that people tend to use are arctangent and hyperbolic tangent, not arctangent. Both of which are sort of shaped like clipping functions. And I was of the opinion that arctangent was the best clipping function out there last time I played my guitar through it. And then when I tried to bench it today to see why that was really true, I couldn't actually see any reason to prefer that to just a cubic polynomial. So I'm going to go try to figure out what the truth is and come back with it next week. Logistic function? What's that?
It's like, I don't know. There's this class of sigmoid functions that I studied when I was doing stuff in neural networks because they're the activation functions.
Yeah.
So what
Yeah, the error function is one of them.
functions, yeah.
Oh, yeah.
Seems like it could be fun to try all those out.
I guess so.
Just in the spirit of things that have E in them.
Yeah.
Right. Intertranscendental. Yeah, I don't know. And I don't know if anyone has actually ever really done a study of this. The truth is that as soon as the signal that you put in is more interesting than a sinusoid, the thing gets too complicated to really analyze very well. And then you're back to modeling those tubes.
And there's no like hard like benchmark that it's all really like subjective. So
As far as I can tell, I mean, all right, so my impression was that the cubic polynomial sounded buzzier, like it had collections of higher buzzy kinds of harmonics, as opposed to just richness, which is maybe harmonics up to 10. And I was thinking that arctan would focus the sound on the first 10-ish harmonics without throwing a lot of energy out in the much higher ones. So I started looking carefully at the spectra today, and I didn't actually confirm that at all. I don't know what I did find, because it turned out that they were different, but it was hard to put. It's hard. I mean, depending on the index and the bias and everything else, there was no rule about how they were different that I could see. So I don't know what the deal is on that. And we may never know. It might just be too complicated to analyze.
Yeah, and like I'm trying to think about how that relates to granular synthesis and windowing functions essentially.
Oh, yeah.
Because it's, this is essentially the same typical thing in terms of shaping something like that.
It is actually, because one way of thinking about it is at least if you put high amplitude stuff in, the stuff just tends to race to the left and to the right and then just be out of range. And so in that case, you're actually really sampling the transfer function itself. You just see the transfer function in the output if you just race past it, without accelerating. So some of that theory should hold over for very high amplitude, just very high saturations. And for lower saturations, I don't know. All right, so since I have web now, first off, here's where you can get all the stuff. Is it there? Yeah, some of it's there. Oh yeah, I'm a little bit behind, but mostly there. And the other thing is, the next thing about nonlinear distortion is controlling amplitude by, instead of doing stuff that is on a line, doing stuff that actually can circle zero without going through zero. And the way you get past zero without going through it is you use complex numbers, which is just basically things that can move in a plane instead of on a line. So I'll develop that up a little bit next time. It's not actually going to be terribly mathematical, as it turns out. It's going to be mostly about staying away from the origin.